Good morning, everyone. Okay, we will briefly discuss about generalized coordinate again, and then we'll move to the virtual displacement, what we are discussing in the last class. Uh, Before going there, do you guys have any question so far? Am I audible to you guys? Can you guys respond if I'm audible or not?
Yes, sir, you are audible.
Okay.
Yes, sir, you're
Yeah. Okay, so let's start this class. So I'll briefly discuss generalized coordinate again. So in the last class, we talked about generalized coordinate and its properties and how to identify these generalized coordinates also, right? And I told you these generalized coordinates, these are basically set of independent parameters that you need to represent the configuration of the system. These are basically set of independent parameters that specify the configuration of the system.
कॉलेज हमने मंगल को अपनी मैसेज आया है
Who is this? Mute.
नहीं हो साहब कॉलेज साहब करूं भाई पर अच्छा था भाई पर लेटा ही
Who is this guy?
सही बात है कंपनी वाले छूट गया है प्रोडक्ट
Mute. Who is this guy? Mute. Configuration of the system. And I told you some of the properties also. And I told you how to represent this generalized coordinate, that they are represented by this symbol Qj, and also these are independent. That these generalized coordinates Qj's are independent. These normal Cartesian or the polar coordinates are not independent of each other if you have some constant involved. But these Qj's are independent even if there are constants. That's why, and also I told you this number of generalized coordinates, those are equals to the degrees of freedom. This is true at least for holonomic system. For holonomic system, number of Qj's, those will be equal to number of degrees of freedom. But let's see what we mean by the configuration of the system. This term, configuration of the system, what does it mean? Little bit closely. So if we go back to this example of this double pendulum, so let's say this is the pendulum system. This is mass m1 and this is mass m2. This angle is θ1. This angle is θ2. So now say these two mass they can make oscillation around this plane. These masses can make oscillation around this plane. So right now, this position of mass M1 and M2, these are represented. You can represent by this term some values of θ1 and θ2. So this is one configuration. This is one of the many allowed configuration. So what are the allowed values of theta will be in this case? Can you guys tell me what will be the allowed values of θ1 in this case? Some of you guys, can you tell me what will be the allowed values of θ1? If you have a simple pendulum, let's forget this. If you have a simple pendulum, then what will be the allowed values of theta in this case? If this is theta, what will be the allowed values of theta will be in this case? How far you can swing this pendulum?
Less than 90.
It will be 90 or more than 90.
Sir, 90 से कम, less than 90 degrees.
So if this top section is blocked, then you can go from here to here. This is plus 90, and in this way also you can go 90 degree, right? And if you can rotate around this swing also, then it will be full 360 degree. So it depends on what are the constants involved in this, how you have designed your thread, how you have designed this rigid support. Depending on that, your theta will be. So from this figure, it looks like that it can go this direction 90 degree, and this direction it can go 90 degree. So these are the allowed values of theta in this case. Similarly, in this case also, you will find these allowed values of θ1 and θ2. So right now, let's say at this particular instance, this mass M1 and M2 are at this position. So this represents one configuration of the system. Now it is also possible that the mass M1 and M2, they are looking like this. Let's say the mass M1 is like this and mass M2 is like this. Okay, and this is the y-axis. So then this will be a θ1, this will be a θ2. So this will be another configuration, right? So this value, the values of θ1 and θ2 here, they will represent another configuration of the system. So similarly, this θ1 and θ2, they together they will represent all the configuration that is allowed by this constant that's involved. That they represent θ1 and θ2 represent those configuration. Okay. And I also told you that this Cartesian coordinates that those can be written as a function of this generalized coordinate, that you can write them as a function of q1, q2, q3. If there is 3n degrees of freedom, you can write up to 3n, and also sometimes these are function of time as well. So you can represent like this. Okay. And then I told you to find out the expression for kinetic energy, to derive the expression for kinetic energy. That you should do as a homework. Now, then we started about virtual displacement, discussing about virtual displacement. Virtual displacement. And I told you that there is, if we write like this dRi, this is real displacement. This represents real displacement. But when we write with this symbol delta Ri, this means virtual displacement. And what are the virtual displacement? We gave definition that virtual displacement refers to an instantaneous. And I told you this is very important. This instantaneous term here, that instantaneous change in the configuration of the system. Configuration of the system allowed under applied forces and constraints. And these two are very important, that this virtual displacement, this is instantaneous, and this should be allowed under the applied forces and the constraints. That whatever changes you make in the configuration of the system, that has to be applied, that has to be consistent with the applied forces. So why this is important, this instantaneous term is important, because I told you that in case of a real displacement is always involved time. You cannot change the configuration of the system without spending any time. For example, of this, let's see this simple pendulum. So in this case of simple pendulum, let's say at some instant the pendulum bob is here at this position. Okay. Now, if you want to displace the pendulum bob from this position to, let's say, at this position, okay. So if this pendulum bob has to come at this particular position from here to here, you need a finite time. It has to spend some finite time, amount of time t, whatever it is, maybe 1 second, 2 second, 10 second, depending on the design of your pendulum. But you need at least some time for the pendulum bob to come here, and that is real displacement that we see in our real world. But in case of virtual displacement, this pendulum bob this displacement will not take any time, because that is basically a imaginary displacement. That is imaginary displacement. That is a purely mathematical concept. So why and also this is one configuration. Let's say this pendulum is here at this particular position with these values of, let's say, theta. So this is one configuration of the pendulum. Now this when the pendulum is here at this position, let's say this is position 1, this is position 2. When the pendulum bob is at position 2, these values of theta, let's say this is theta 2. So these represent another configuration of the system. You can also have the pendulum bob, let's say, at this position. Let's say this is position 3. You represent this by theta 3. So this is another configuration of the system. So virtual displacement means that the pendulum bob changed its configuration, but it does not involve any time. It happens instantaneously. Instantaneously, this pendulum bob comes from position 1 to position 2, or position 2 to position 3, or any other configuration, which are allowed under the constraint. What are the constraint here? Constant here is that this string is inextensible. This L is fixed in this case. So that is one of the constant here. So pendulum bob, all the configuration will be along this line. So you cannot imagine an instantaneous displacement here, in which case the pendulum bob comes here. Let's say the pendulum bob comes here. So this is not an allowed configuration, because in this case your L will be much longer. So this is not allowed. This is not allowed. But you can imagine any displacement, any configuration along this line. So that will represent a virtual displacement. Okay. Or if you can also imagine similar situation in this example of double pendulum also. That this is one allowed configuration. Let's say this is configuration 1, this is configuration 2. So in reality, if you want to go from configuration 1 to configuration 2, you have to spend some time, some finite amount of time. But in case of virtual displacement, you come from this configuration 1 to 2 without spending any time. That is instantaneous. But it has to be an allowed configuration. That it has to be within the allowed values of theta 1 and theta 2, and also this within this allowed values of L1 and L2. So that represent a virtual displacement. Okay. Now from virtual displacement, we'll derive some important conclusion. So one is called principle of virtual work. One is called principle of virtual work. Who has sent a message? I gave you just now, I gave you example. These are imaginary. You can imagine. These are basically, I told you, change in the configuration. It does not happen in reality. Yes, time is 0 in case of virtual. You guys should ask. Don't send in chat. Why you are not? You guys are not speaking. It is always preferable if you guys speak. Okay. Okay. So we will come to the principle of virtual work. Okay. So what is principle of virtual work? So let's derive the principle of virtual work a little bit. Okay. So now let's consider you have a system of particles. Okay. And then the total force. So let's consider a system of particles. Okay. System of particles. Okay. Now then if you know the total force that is active on the ith particle, you know the expression total force acting on the ith particle. This will be represented by Fi. Okay. And what are the component of Fi? So you can write Fi. This is basically the externally applied force. This plus the force, let's say Fi. This is the applied force. This is the applied force, and small Fi. These are forces due to constraint. Okay. Forces due to constraints. Okay. So now when the system is in equilibrium, then the total force acting on the ith particle or any particle, that should be equal to 0. Okay. So if you consider the system is at equilibrium, if the system is at equilibrium, then you can write Fi, this should be equal to 0. Okay. Now then the total, then you can see if this force Fi, how much work it is doing in creating the virtual displacement delta Ri. So that is called virtual work. So you can calculate virtual work done by the force Fi in creating virtual displacement. In creating virtual displacement delta Ri. So you have the total force Fi and you are creating a virtual displacement delta Ri. So in reality, if you know that you are displacing the system by delta amount, the total work done, then you know dW is basically Fi dot dri. It will do some amount of work, and that was defined by Fi dot dri. Okay. So similarly, virtual work. So virtual work done by this force F, so that should be equal to Fi dot delta Ri. So that is the virtual work done by the force Fi in creating this infinitesimal virtual displacement delta Ri. Now, if the system is in equilibrium, then if you do sum over all this particle, then this total work done, virtual work done, that should be equal to 0. Okay. Now, if you then write down this component of Fi, so Fi is basically Fi applied plus small Fi. So this you can expand as Fi externally applied dot delta Ri plus this forces due to constant dot delta Ri. Okay, this should be equal to 0. Now there is an important concept that these forces of constant, they do not do any work. This term is generally is equal to 0. When the system is in equilibrium, these forces of constant, they do not do any work. This is considered. This is our consideration. That let's consider this Fi dot delta Ri. This is equal to 0. Okay. Then from this we can write Fi E dot delta Ri. This is equal to 0. This is called principle of virtual work. This is called principle of virtual work. Now in statement, what you can write? You can write that at equilibrium, virtual work done by the applied forces is 0. Okay. This is called principle of virtual work. Now we have considered this term is equal to 0. But can you guys tell me with some example where this term is not 0? That forces this term Fi dot delta Ri, Fi dot delta Ri. I told you that the work done by the forces due to constant, that is generally 0. But can you guys tell me in some cases where this won't be 0, this value? Anyone? Or can you guys tell me why we are considering this term is 0? Okay. So let's say that we have a sphere, okay, and this is mass m, okay, this is mass m, and this mass m restricted to move on the surface of the sphere. So can you guys tell me in which direction the forces of constant are acting in this case? That this is a three-dimensional sphere and mass m is restricted to move only on the surface of the sphere. Then what are the forces of constant and what is the direction of that force? Can you guys tell me?
Towards the center of sphere.
This is the center of sphere. Let's say this is the center of sphere. At the center. Then this mass m is restricted. You guys can think that you have let's say you have a football and you restricted let's say one cricket ball to move on the surface of that football. Then which direction the forces of constant is applied in that case?
Sir, at the
Towards
center of
center.
the ball,
Hmm?
centripetal force.
You
Towards
can
center
think
of the ball.
it can be
Towards the center so
centrifugal
that
force.
it cannot
Yes.
fall.
So in general, you can say that this force is radially applied, right? That this is either radially upward or radially inward, right?
Downward. Yes, sir.
But if so, this is the direction of force. This is the this is the force, constant force in this case. And what is the direction of allowed displacement in this case? If this mass is moving on the surface of the sphere, then what is the direction of movement?
Tangentially, sir.
Tangential direction.
So this will be tangential, right? So this will be move along this direction. So this will be delta Ri. So what is the angle between this force and this displacement?
90 degrees.
Sir, 90 degree.
So if you calculate Fi dot dri, this should be equal to
0.
0. So in this case, you can tell that this is forces of constant, they do not do any work. So this is one example. So can you guys come up with similarly that one example where these forces of constant do not does some work? It so for as a hint, it has to be a dissipative system. For a conservative, not a conservative system, but a dissipative system, it has to be. If you have, let's say, frictional force, then this term will be zero or not. F dot dr will be zero or not if you have frictional force involved.
No, sir.
No, sir.
It will not be zero, right? So, for
Yes,
example,
sir.
if you have this incline and if you have a ball that is rolling, and this is not, there is some friction involved. So, direction of friction, it depends, it is opposite to the movement, right? And so if displacement is along this direction, the friction will be also parallel to this displacement. So it is not 90 degree, it is always parallel, right? So in that case, this term will not be zero. Okay. So this is just a consideration that Fi dot delta I equal to zero. It don't have to be zero always. Okay. That forces of constant do not do any work. So this is principle of virtual work, and this is applicable in case of a when the system is in equilibrium. Okay. But now we'll do another derivation, which is called D'Alembert's principle. Okay. That is called D'Alembert's principle. And in this case, system is in dynamic equilibrium. Okay. System is at dynamic equilibrium. Do you guys know what is dynamic equilibrium?
Yes, sir.
I'm moving with constant velocity.
Moving with constant velocity. Yes, that can be an example of a dynamic equilibrium. Yes. So one example is that right now it is raining here. Okay, and you know these raindrops, they like when they come from this cloud, so their size constantly get increases, right? This raindrop, they merge with each other and their size increases. But at certain point, the size becomes constant. Their size becomes a constant. Okay, size and velocity becomes constant. Why that is constant? You guys know this raindrop.
रेजिस्टिव फोर्स के वजह से
This is one example of dynamic equilibrium, because what happens, these raindrops, the forces, there is a gravitational pull on these raindrops, right? And that is their mass into acceleration. Okay, but these raindrops, they are also facing this air drag, because when these raindrops, they are falling down, because of viscosity of air, there is some forces acting upward direction also, right? And this is because of air drag or air viscosity. So when these two forces are equal, then this raindrop will reach certain constant velocity. And you can say this is in dynamic equilibrium. But if you drop a stone, if you drop a stone, that will ever reach in a dynamic equilibrium or not?
No, sir.
It will not reach in a dynamic.
No, sir.
So, but in both
Understood.
cases, this equation is applicable. That force is equal to rate of change of momentum. This is applicable in both the cases. This is Newton's law, right? That force applied on the ith particle is equal to the rate of change of momentum for the particle. This is applicable for this case also, raindrop, and this is also applied for stone also. But this raindrop is in dynamic equilibrium, but this is not in dynamic equilibrium, this stone. There is not enough viscous drag to reach this dynamic equilibrium. Okay. So what you can say from here, that Fi minus Pi dot, this is equal to 0. Now if you multiply this by delta Ri, that will, what will get? If you multiply this Fi minus Pi dot with multiply with delta I, this is still 0. Okay. Now Fi you can again write in terms of Fi E, that is the applied force, that is Pi dot delta I, plus there is another term, that is Fi dot delta, small fi, right? This we just simply write Fi equal to Fi E plus small fi, and this term is 0. We told you that this term is 0. We can consider. Okay. So if we consider that these forces of constant do not do any work, then we can write from this equation. Okay, here basically we are summing over all the particles also. Okay, this is not for a single particle. So we can write again Fi E minus Pi dot delta Ri, this is equal to 0. Okay, and this is called D'Alembert's principle, that when the system is in equilibrium, this externally applied forces and the rate of change of momentum, if you multiply that with the virtual displacement, that is equal to 0. That is D'Alembert's principle.
So if we are taking Fi 0 in all the cases, so why are we considering it? Matlab,
So I
in
told
what
you
cases we
these
have-
are some theorems. These are some theoretical statement. Okay, and this theoretical statement always involves some assumption. So this is true under these assumptions. If you
Okay.
don't take this assumption, you can go ahead. It's not a problem. But these are valid only under this assumption. Okay.
Okay.
Sir, what this principle states?
So this is basically what you see from this statement, that when the system is in dynamic equilibrium, this term is always 0 if the system is in dynamic equilibrium. When it is static equilibrium, then then the principle of virtual work is accurate, that if you multiply it by Fi dot delta I equal to 0. But if it is in dynamic equilibrium, then you have to consider both the applied force as well as the rate of change of momentum. So basically, principle of virtual work, it represents the static system. But in D'Alembert's principle, then this represents the dynamics of the system. Okay. So one is static and another one is dynamic. Okay, from this we will derive the Lagrangian equation of motion. Okay, I will not do the full derivation. It is there in my note. I'll only give you the key step. If you guys interested, you can check. But we will not do the full derivation there. From this D'Alembert's principle, we'll derive Lagrangian equation of motion. Okay, we'll derive Lagrange's equation of motion. We'll derive Lagrange's equation of motion. Okay. So we'll start from this D'Alembert's principle. Okay. We'll start from this D'Alembert's principle that Fi E minus Pi dot delta Ri, this is equal to 0. Okay. Now we want to find out the expression for delta Ri. We need to find out what is the expression for delta Ri. Okay. So we know that Ri, this you can write Ri in terms of the generalized coordinate, that Q1, Q2, and dot Q3 T. Okay. And then I also told you in the last class, you can write Ri dot, this will be equal to J del Ri del Qj dot plus del Ri del T. This is for real displacement. This is real displacement. This is dRi by dt. Okay. But when we have virtual displacement, then that is instantaneous. Then there is no t term will be there, right? So this term, this del Ri by del T, this term will be 0 in case of virtual displacement, because that is instantaneous. There is no change in time involved in that case. Okay. So in case, so similarly, we can write delta Ri. This should be equal to J del Ri del Qj into delta Qj. So we wrote the same expression. Only thing is that we have not considered. We have considered this del Ri by del T. This is 0 because this change in this virtual displacement, that does not involve any change in time. That is instantaneous. Delta T is 0 in this case. Delta T is 0 in this case. So there will be no this del Ri by del T term. Okay. So now what happens if we replace this term here? So if you replace this delta Ri in this equation, so if you replace this here, what we'll get? So if you replace this here, so we'll get I Fi E, then this will be dot product with this term del Ri by del Qj, delta Qj, right? It will be del Ri del Qj, delta Qj. This will be one term plus you will have Pi term, not plus. This will be minus. This will be minus. You also have the Pi dot term, right? So you will get Pi dot and then del Ri del Qj delta Qj. This should be equal to 0. Okay, what I have done, I have simply replaced this delta Ri here by this expression of delta Ri. Okay. Now from here, what we can write? We can write J Qj delta Qj minus Pi dot delta Ri del Qj delta Qj. This is equal to 0. And what is Qj? At this term I have written as Qj. This term, this I have written as Qj. Where Qj, this is basically equal to Fi dot delta Ri delta Qj. Okay, here this should be both index I and j, not the one index. One index for I and one index for j. One index for j. So this should be I and j index. In case of Pi also, this will be I and j index. And here also I and j index. Okay. And what is Qj? This is called generalized force. This is called generalized force. Okay. So I have not done much here. So what I've continued with D'Alembert's principle, and then I have replaced this delta Ri by this expression for delta Ri. This expression here. Okay. And then I wrote that Qj is equal to Fi dot delta Ri by delta Qj. And this Qj we call that this is generalized force. Okay. And then I'll skip the rest of the derivation. Okay. From here, from this here, you can derive. And this is in my note. I'm not going to derive here. But if you guys are interested, you can check. And if you guys have question regarding the derivation, you can ask me. Okay. But I'm not deriving that thing in the class. Okay. You guys can check the note. But yeah, you guys ask me if you guys have any question regarding the derivation. Okay. So from this expression, you can write the d dt of delta t by delta qj minus delta t, this is dot, del qj, this is equal to qj. Okay. What is T? T here is the kinetic energy. T here is the kinetic energy. Okay. Now T is kinetic energy, and we can further simplify this expression. We can further simplify. Qj is I told you Qj is basically generalized force, and Qj you can write Qj equal to Fi dot delta Ri by delta Qj. Okay. Let's say this is equation 1. Okay. So Qj is generalized force. Now let's say Fi is conservative. Fi is conservative. That this is a conservative force. Okay. Then you can write that Fi equal to minus gradient of I into V. Then from here you can write Qj equal to Fi is basically gradient of IV dot delta Ri by delta Qj. And this term, this you can write minus del V del Qj. Okay. This is over I. Okay. And then if you replace this expression for Qj in equation 1, then if you replace in this equation 1, okay. If you replace this Qj equal to minus del V del Qj, then from equation 1, what we'll get? From equation 1, we'll get d dt of del t del Qj dot minus del t del Qj. This is equal to minus del V del Qj. Okay. This is what you will get. And then you can further write d dt of del t del Qj dot minus del t minus V del Qj. I took V this side, so this will be t minus V. Okay. So this will be equal to 0. And then you can further write d dt of del t minus V del Qj dot minus del t minus V del Qj. Why I am included V here? Because V is not a function of Qj dot. Okay. V is generally not a function of Qj dot. So this del V del Qj dot that I have inserted, this should be equal to 0. Okay. And then we can write d dt of del L del Qj dot minus del L del Qj, this is equal to 0. And this is the Lagrange's equation of motion. This is the important formula. Okay.
So why you have done T minus V in this?
Where this second term or the first term?
Yes, the second one.
Second term, this is del t del Qj. If you take this side, this will be minus here. So if you take this del V del Qj on the left hand side, it will be plus del V del Qj, right?
Yes, sir.
So then you can write del t minus V del Qj. This expression is basically what? Del t del Qj plus del V del Qj. So I have combined here. This is here.
And sir, what about this third one, third line? This
one? Here.
Yes, sir.
So here
Yes,
what
sir.
I told you that if V is not a function of Qj dot, then what del V del Qj dot will be 0, right? If V is not a function of Qj dot, then del V del Qj dot, this will be 0. So this what I have added here, that minus del V del Qj dot, this is basically 0. So I have done simple some mathematical manipulation here. Okay.
Yes, sir.
That's why I don't wanted to do any derivation here. So you don't, if you don't want, you don't need to remember this whole thing. Okay. But this little bit you should remember from del t, from this part, del d dt of del t del Qj dot up to here, this small derivation. But the large section of the derivation I have not done here. That is in my note. You guys, if you want, you guys should check. Okay. And this is called Lagrange's equation of motion. This is Lagrange's equation of motion.
So this derivation can come in exam.
From this small section can come, whatever I've done here, from from this part to this.
Okay, sir.
Okay. And what is L? L is basically T minus V. You can see from here. Yeah, this part I called L. Okay. So this is, I replace T minus V by L. So this is del L del Qj dot. And this is called Lagrangian. This is called Lagrangian. Okay. This L equal to T minus V. This is called Lagrangian. So T is the kinetic energy. T is the kinetic energy, and V is the potential energy of the system. Okay. But this expression you guys should absolutely remember. Okay. This expression of the Lagrange's equation of motion, the d dt of del L del Qj dot minus del L del Qj, this is equal to 0. This is also one form of Lagrange's equation of motion. Okay. Where is that? This where I wrote this del T form. This equation 1, this is also one form of Lagrange's equation of motion. Okay. But here what is the problem is that Qj we have not yet inserted that the Qj, these forces are conservative. If the forces are not conservative, then you have to work with this equation 1. This is also Lagrange's equation of motion. We have further simplified considering that the forces are conservative, so that we can write in this nice form del L del Qj dot. Okay. So I'll give one example. So how to solve problem using this. In next class we'll do several problems to get you familiarized with this Lagrange's equation of motion. Today I'll give you a quick example. So let's say you have a linear harmonic oscillator. You have a linear harmonic oscillator. So for this will be a linear harmonic oscillator. Let's say you have a mass m. Okay. And that mass m is attached to a string. Okay. Of force constant F. So what this will be one example of a linear harmonic oscillator. So what this mass m will do, like this mass m will vibrate along this plus x and minus x direction, right? So if you pull the string, in the plus x direction, then the spring will try to come back to its original position. So the forces will be on the negative x direction. So when you pull the mass along positive x direction, the forces of the string that will try to get back the mass in its original position. Similarly, if you try to compress the spring will give a force to pull out from that compressed position. So this is also one example of a linear harmonic oscillator. So can you guys tell me what is the kinetic energy in this case? Let's say this is along x direction. Okay. Can you guys tell me what is the kinetic energy in this case? Let's say this mass m is displaced by amount x. Okay.
Half kx square.
Half kx square, that is kinetic energy or anything else? Kinetic energy means what? Half m v square, right?
Sir, half m omega square a square.
half mv. What is v? V here is simply x dot. dx dt is velocity, right? What is the expression for kinetic energy? Half mv square. So here v is basically x dot, right? Or dx by dt, that is velocity. That is the kinetic energy. What is the potential energy? Somebody already told that that is half
Half x square.
x
Half
square.
k.
So what will be the Lagrangian in this case? Lagrangian is basically, I told you, t minus v. So t is, in this case, t is half m x dot square
Minus
minus
half k square.
half k x square. This is Lagrangian. So then what is the value of del L del x dot? Now in the Lagrange's equation of motion, we have del L del qj dot and del L del qj. We need to find this derivative. So what is the general, okay, so before going there, what is the generalized coordinate here in this problem? How many degrees of freedom we have in this case?
One.
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 DOF is 1. And what is the generalized coordinate in this case?
1.
No, generalized coordinate. What is the generalized coordinate in this case?
X.
Generalized
X, sir,
coordinate is
X.
simply x. If you know x, you
X.
know everything here. Okay. So we need to find del L del qj dot. Del L del qj dot is basically here del L del x dot, right? Because qj is equal to x here. Here x is qj. So what is del L del x dot here? Del L del x dot is basically m x dot, right? And what is del L del qj? That means del L del qj is del L del x. And what is the value of del L del x? That is basically minus kx, right? Okay. So this Lagrange's equation of motion, we know d dt of del L del qj dot minus del L del qj, that is equal to 0. So in this case, we can write d dt of del L del x dot, because qj dot is x, and del L del x, this is equal to 0. So what is del L del x dot? That is basically m x dot minus del L del x is basically kx. This is equal to 0. So what we get from here? mx double dot plus kx equal to 0, right? Or you can write m d2x dt2 plus kx equal to 0. Is this familiar to you now? Or you can write d2x dt2 plus k by mx equal to 0. And this is basically omega square, right? This is what is the equation for equation, this equation. This is the equation for linear harmonic oscillator, right?
So what is the meaning of double dot on x?
Double dot means, okay, so whenever I write something dot, x dot, that means dx dt. If I write x double dot, that means d2x dt2. Okay.
Okay, sir.
So is this familiar to you guys? This looks like equation for a linear harmonic oscillator or not? Can you guys?
Yes, sir.
Okay.
Acceleration का ही तो.
So what we got? So earlier in class 12, you get to know some different method using which you can derive this equation for linear harmonic oscillator. So what we are doing here, that by using this Lagrange's equation of motion, this Lagrangian formalism, we are deriving the same equation. Okay, but this Lagrange's formulation is superior, and why it is superior we will tell you in the next few class. I'll tell you why this method is superior compared to this Newtonian dynamics or whatever you have read so far. So for now, it looks like it's more complicated. It involves more complicated calculation, more detailed calculation, but it has its own advantage. And I will tell you in next few class why this is superior. But before going there, we'll do some more example of this to get you guys familiar with this Lagrangian method. So whenever someone asks you to find out to do this derivation or solve a problem using Lagrange's method, what you have to do, you have to find out the potential energy and the kinetic energy in terms of the generalized coordinate. And then you write down the Lagrangian as a T minus V, and then you apply this equation, Lagrange's equation of motion, to get to this problem. So we are not doing solution, you can see. We are just building the equation of motion. Next step is the solution, that is different part. So before solving anything, we first have to formulate the problem in terms of the differential equation. So we are doing that step. That we are deriving, we are building the problem set. In this case, how to solve the problem. Okay. So in the next class, I'll give you some two, three more example. Okay. And yeah, do you guys have any quick question? Okay, again, it's almost time now. Do you guys have any quick question?
Sir,
Yes.
sir, why we have to describe that quantity, sir, virtual displacement?
But you see, this is a theoretical concept, and using that virtual displacement, we came to this Lagrange's equation of motion. That we took the help of this virtual displacement to derive this Lagrange's equation of motion at this point. So that's why I told you this is a theoretical part. That based on this theoretical framework, we get to solve the problem. Any other question? Okay, if not, then let's end here. Tomorrow I'll discuss some more problem related to this Lagrange's equation of motion, and then we'll do another framework, Hamiltonian, to do the same thing, but you will see that